Time's up. Time's up. So, looking at this form of question here, like we've been doing volumes of revolution in AB, and we're talking today about integrals that will kind of some different varieties of integrals that we're going to see. One of these is related to an extra credit that was on the last chapter test. That last one about how far the bike moves. That I don't. If you could have got it right, I don't think anybody got that one right. Yes, some people did get some partial credit on it. It's related actually to integrals that might have an upper limit of infinity, which is really what we see here. So first, I'm kind of titling this like an infinite Hershey kiss. And if we think about the three-dimensional shape, that, right, we've got this kind of sweeping in, it'd be like a Hershey kiss kind of on its side, but the point goes on forever, right? That's really what this says, because if the interval is from 1 to infinity, and this function, root 3 over x squared, doesn't it have a horizontal asymptote of 0? Right? Think the degrees, right? Denominator's bigger, you should nod. That's pre-calc. That's not even calculus. So this is going on forever. Now, sometimes the first reaction of people is just want to say that this integral would just be infinite. It's just going to diverge. What about the function makes you think there's probably a sum to this? Now, there is a little bit then of a paradox, right? I have a shape that's going on forever, and that means it's going to have a volume that's fixed. What about the function, Julia, might make you think, I think there might be an answer to this? What series are you thinking of? And what test would you use to confirm it? Okay, so you are right that a corresponding series here could be convergent because Siri, what are you thinking? Yeah, so we could go there to the limit comparison test because 1 over n squared, but you could really, that square root of 3, you could like factor out and just say what? P series, which is really what you just argued as well, saying that 1 over n squared is going to converge. So in other words, if this curve, thinking about the points that we were talking about, like when we think about the series, there are just certain points on here, right? You know, there's a point corresponding to when x is 1 and when x is 2 and then when x is 3 and when x is 4, right? Like we don't get all the values in between, but there's probably something that would make you think that if those points are going to converge, right? If we're going to say that's convergent, then the integral would probably be as well. Like we could maybe think about what the integral of all of this would be. So here's what we're going to do. We could write this, and on your 89 or even Inspire, you can actually type this integral in, right, Natalie? You can say the integral from 1 to infinity. Don't do it now. Do it later. But like you can put something like this into your calculator. Now I don't have the right answer here yet because I don't have volume right now. So I want to kind of fix this first to kind of make this the volume. Basically, if I wanted to make a Hershey Kiss like this, how much chocolate would it take? Right? Volume of chocolate. Tell me the cubic units of chocolate that would take to construct a Hershey's Kiss that had this infinite point going off away from us. So fix it for me. So I need a pi, yes. And square this. Why am I squaring that? It's the radius. This is the disk method, right? Like thinking about what we have. Now, you can put this in your calculator, but this would easily be a no calculator question. So let's think about squaring it. Which would be this. Couldn't you find the antiderivative pretty simply? So what's the antiderivative of negative 1 over x cubed, I think is what you said, Nene. Is he right? Yeah, he's already canceled those 3's out, I think, there. So, and this is the thing. So we need to take this answer times pi and evaluate this from 1 to infinity. Now, as I'm writing this, it should feel kind of odd the way I'm using the upper limit and using the infinity symbol here. Now, I'm showing it because this is probably what some of you were writing down or thinking. This is not awesome mathematical notation, but it's a notation that people would understand, your calculator understands. But it's not an ideal notation just because infinity is not a number, which means the moment I'm writing infinity there, what am I actually also then doing? A limit. There really then is a limit involved here as the upper limit goes to infinity, right? Infinity is not a value to consider. So, but as I look at this, Richa, you said that this answer is pi. Can you tell me algebraically why this ends up being pi? Minus 1, yes. And so the reason that this part is 0 is like, again, we know that that should be going to 0 because we've talked about convergence of that, or we could think about horizontal asymptote there, but 0 minus 1 times pi. Final answer, pi. Now, if you wanted to have a little bit more sophisticated, mathematically precise notation, it would actually look like this. It would be the limit as b approaches infinity of, well, we could put the pi on the outside, but if I would just write it like this, it would be the integral from 1 to b of pi times root 3 over x squared dx. So this is really what that is saying. Now the advantage of using the b there in this upper limit is that, notice that like here, like when Richa is saying that first part's 0, it's true, but it's not really a very precise way to say it's true. Well, if the denominator gets big, then the fraction goes to 0. Do you notice that if I would write it out this way, using...
This is a reminder that the faculty and staff forum with Dr. Cashman is at 3:30 in the UM library.
So notice that it would be something that looks like this. The limit as b approaches infinity of this whole thing. So I'd like you to start writing down like this, like you can write this down if you probably should already have that in your paper, but write this notation, and I want you just to see why writing that limit might be helpful to argue some of these questions. It doesn't really change the work, it doesn't change the reasoning, like what we're saying here that this answer is 0 is still going to be true. But notice that it becomes a little bit easier maybe to argue why it's 0, just what we understand about limits. So we're going to have the limit as b approaches infinity of pi times negative 1 over b cubed minus a minus, so add pi times 1. And then here's really that logic that the limit as b goes to infinity of this piece, like that's like saying x goes to infinity of 1 over x cubed, right? Like that's that horizontal asymptote conversation. That piece is 0. So this piece drops out. This limit doesn't affect this answer. The answer is pi. Again, the answer doesn't change, but this is the more precise notation. Honestly, like I write this, but you should definitely know that when you're writing that, you're really writing a limit. So when you get to this step here of substituting in infinity, like again, you can't substitute infinity, so you're really taking the limit as the upper limit approaches infinity. So if you have that logic, you won't really go wrong with it. So the volume of chocolate necessary would be pi cubic units. Okay. Questions, anything I said so far? I think that they wouldn't love you to write that. If it's on a multiple choice question, nobody cares, right? Just write it, think it, get the right answer, whatever. I'm going to guess that if it's on a free response, they're going to want to see that you're actually taking the limit. So that's why I'm saying that this is the precise notation when we're thinking about when the upper limit is infinity. Okay. About new problem. So going back to even just finding the antiderivative. So again, don't pick up your calculator for this. This would be a no calculator question, so fair warning in advance. The integral from 0 to 3 of dx over x minus 1 to the 2/3. Okay, so I'll kind of work it here with you. So let's suppose that we approach this problem the way we approached every question up until now, though there is a serious, significant wrinkle to this problem. So what I am doing here is not right. So don't write this down, but this is probably what most of you would do if you'd solve this question. This is x to the negative 2/3. So I should increase the power by 1, divide by the new power. So this is going to be x minus 1 to the 1/3. I'm going to divide by a third, which is multiplying by 3. I'm going to evaluate this from 0 to 3. So I'm going to substitute in 3. So I get 3 times the cube root of 2. I'm going to substitute in 0. I'm going to get, so minus 3 times that cube root of negative 1, which is negative 1. So something that, hopefully I did the arithmetic right, everything good there. But I'm saying something's wrong. Look at these limits for a second. There's something that could have been going on here that we really should have been much more careful about. And look at this function and think about domain. Anybody notice something? Tell somebody next to you, what are you noticing that should have made us pause before I ever did this? Looking at these limits and thinking about domain, I should have said, ooh, what if? Talk to somebody. I put in Desmos here. And we were interested only from, so I should include the restriction here, so from 0 to 3. And I'm looking for this area, right? Isn't that what we're after? The integral would be the area. See the problem? That there is a discontinuity in the middle of this interval, right? There's a vertical asymptote that's in the middle of this interval that I'm interested in. So if I'm trying to find the area, it's easily possible that the answer could have been infinite. Let's think about like why there would be answers that would be infinite versus getting an answer like with Hershey Kiss that we just drew. Like, doesn't it depend on like how fast the function gets close to the vertical asymptote? Like, we think about convergence in the p-series test. We talked about, well, how fast is it getting close to 0? So n squared gets close to 0 faster than 1 over n. And so how fast am I getting, how quickly is it approaching that vertical asymptote is going to matter. Sometimes I could get answers, sometimes I could get infinities. So really what has to happen for a question like this is we have to break this apart in order to understand it. So I'm going to just take a snipping here of this and dump it in. Oh, I did have a link. So I just remade that real quick. I forgot I hid it from you. So here's what I want you to try to do. So we know at 1 there's a problem. Okay? Now think about properties of integrals. Like if I'm looking for the integral from a to c for some function, I could definitely think about the integral from a to b plus the integral from b to c, right? We saw that long time ago, early January, about a property of integrals to split them apart. So what if we try to take this in pieces to be sure that we understand what the area here would be? So I'd like you to try this. We're going to integrate from 0 to 1 of the function. Okay. Now, when you're thinking about this value of 1, that the function is undefined there. So again, do you notice that there's a notion of a limit that's sitting right here? So what if we said we're approaching b and we're thinking about the limit as b approaches 1? So much like the last question, and then I add to that the other one. So why don't you try it? So using what we just talked about, can you think about breaking this apart and try and decide if the sum really exists or not? Work together, see what you can do. Okay, so when we were looking at these integrals as we divide them up, like this is really the first one that we have to sort out, isn't it? Like we want to go from 0 to 1. And so I'm saying A or B, you can choose whatever you want. I think I wrote B up there, but like notice something about this limit though. Like this might influence some of our choices at times. Like why do you think I wrote that? I'm only coming from one direction, right? I'm moving from 0 to 1, which means I'm approaching 1 from the left. So the work here is going to look really pretty similar. Like I'm going to take the limit as a approaches 1 from the left. So I'm going to find the antiderivative. We already did that. So this is x to the negative 2/3, increase the power, divide by the new power. And we're supposed to be evaluating this from 0 to a. And then we should do something similar with the integral on the other side. So we're going to be going from a to, was it 3? And we're going to find the limit as a is approaching 1. But that has got to be from the right, right? If you think about the interval from a to 3, you can only get to a in that scenario from one side, right? We're skipping. Do you notice that we're basically skipping over the asymptote here? Like as we're doing that, we're approaching it really from both sides. The antiderivative here is going to be the same. So we now have the limit down here, the second piece. Same antiderivative. Evaluated though from, in this case, a to 3. So if you didn't have something like this, like I think what I'm going to do is I want to show you some generic kinds of scenarios here that could come up. So really the task then would be to, we're going to substitute in A, minus, substitute in 0, and then take this limit. Noticing here that A is approaching 1 from the left, okay? So if we're approaching 1 from the left, do you notice that this piece, x minus 1, would always be what kind of number? It would always be a negative number, okay? Maybe we should finish it. Should we finish this? Like, I think you're looking at me like you're nervous about it. Okay, so limit A approaches 1 from the left. Are you writing this down with me? So we're going to have 3 A minus 1 to the 1/3 minus 3 times A minus 1, I'm sorry, 0 minus 1 to the 1/3. That's the first piece here. So I'm going to have the second piece. So what does this turn out to be? So this is always negative, except there's this 1/3 that's happening. We're getting closer and closer here to what number as I get closer to 1 from the left? Getting closer to 0. So what is that whole thing? It is 3. Right, this piece is dropping out. This is a cube root of a -1, but there's another negative, so it's 3. Okay, so if you did not get that, who got that half of it? Good. So you should have something like that that's happening over here now, which means you should have a second half to it. Do you want to try that? So try that. I'll give you a minute. If you didn't get that first part right, see if you can sort out the second piece. So this actually should be what you have, and notice that you might be looking at this and going, wait a minute, isn't this what I had sketched out a minute ago? So here's what that then means, that in this problem, it didn't affect our answer, which must say something about how it's converging along this asymptote. But there was no way really to know that before I did it. Like, I'd have to either have an analysis thinking about these powers here to make sense of it. So here's the issue then. Sometimes you can luck into a question like this and get the right answer by ignoring it. And then there's other times what easily could have happened here is that it would look like there's an answer, except when you go to do these last pieces here, this ends up being actually infinity, which means the whole answer is infinity. But without thinking of the limit, it's disguised, you're not going to see it. So here's what I want you to recognize then. If, and this would be a good summary to put in your paper somewhere, that if across the interval for the integral, we are crossing a vertical asymptote, we have to break the integral into multiple pieces. So you need multiple integrals if you're going to cross a vertical asymptote. And then you think really about the limit that's involved with them. Otherwise, it could mislead you into getting the wrong answer. So all of these today are kind of falling under a certain category of improper integrals is how I title it. So if you want to title your notes that, create your corresponding table of contents as improper integrals. Okay. Now, and so what I have here are just a couple examples of really what we've seen in terms of, like, these three here are really corresponding more to like the infinite Hershey kiss kind of example. So if I'm interested in an interval that's going to infinity, again, we could write this, but the more precise notation is the limit notation that we're using here. Okay, I'll erase that if you're wanting that. Notice that it wouldn't be a lot different if I wanted to integrate from negative infinity up into a number. I would just make the lower limit negative infinity, and I would really, again, I'm taking a limit that's involved. I could actually have both limits that would be infinite. And then notice here, that's what's unique maybe about this one. When you read this, do you recognize that that's a property of integrals? That I could break it again, right? I can pick some random moment. If I integrate up to this number, so let's say 0, and then I integrate from 0 on, shouldn't that sum up to be the whole answer? So they're showing that broken apart. You actually wouldn't have to do that. Like, you really could just think about having the upper and lower, and you're taking a limit of both those pieces. So all of this here is really corresponding to that like infinite Hershey-Kiss kind of example of limits that are at infinity really are some limit as that value is approaching infinity. And then let me put up this, I think I have a summary here. Thought I did. Looks like I don't have my summary of the vertical asymptote. I'll have to fix that here in a minute. Why don't we try one of these while I make a nice summary there for the vertical asymptote one. But so here's one, the upper limit's infinity. Again, you can write it that way. For me, that's fine. Mathematically precise, the upper limit should be b. We're integrating to b. The limit is b approaches infinity. But just like when we think about convergence or divergence, like this could not exist. Now, as you're looking at some of these, I do want to remind you that like this is probably a no calculator question, okay? So how would we integrate this? What? So it is one of those. So if that's it, then do it. So that's good review, integration by parts, if that's what it is. If you don't know, ask your neighbor. It is. Okay, let's see how we're doing. Ready? Time's up. On screen. So, integration by parts. U, dv, make the right choice, flip it, right, all of that. And it should take you to, notice here that I'm writing it from 1 to b. And so I just kept writing that limit here off to the side, but here is the antiderivative sitting right here. Why is it minus? Well, there's a minus from minus the integral of v du. There is a minus here already. The antiderivative would produce another minus from that exponent. There's the 3. And there's our antiderivative. How many of you got the antiderivative right? That's not. So integration by parts definitely can get wrapped up into other questions like this on the test for you. Okay. So now we need to do the limit as b goes to infinity, or this is our upper limit of infinity. And so really, if I would just try to write it out, right, I'm going to substitute in a b minus substitute in a 1. And it's the limit as b goes to infinity. And if I just try to clean that up, remember that there's a property of limits that would, couldn't I like separate this into a couple pieces if I wanted to? And so that's really what I've done there. This is just that second part of it. Now, here's the thing. This piece that comes from substituting in the 1, there's no b over here, right? Which really means that this limit is going to have 0 impact on that second calculation. With me? So, we need to figure out what this is. And then we're going to add 2 over e. John, did you find your mistake? Okay. Was it right here in green? John, what does this boxed part turn out to be? It is 0. Can you prove it? Any question? Answer. Okay. Okay, so if I rearrange it a little bit, it would actually be this, right? Like, so the e to the negative b, like, so you were thinking about, I think, just this first term, but I could kind of combine the second term with it because it also had an e to the negative b. So that's what I did here. But you're right. We can think about like the rates of growth between these functions. So you could make an argument from rates of growth. Don't we know the exponential should grow faster than the line? Doesn't that force it to go to 0? Now, if you forgot that, tell me the other thing that we know that would prove that that limit is 0. So John says he thinks this is 0. Tell me another way that we could prove it easily. Rates of growth. Like, so rates of growth are like the denominator grows faster than the numerator, so it's going to force it to 0. There's a much simpler way that we could argue it. Simpler. Yeah, I think that is simpler though. So L'Hopital's rule takes the derivative of the numerator, takes the derivative of the denominator. Doesn't the numerator then really just become a constant? And then the denominators, then we can see this piece goes to 0. There's the final answer. Okay. Who got it right? Anyone? Good job. So close. John was really close too. So let's do another one. So I'm also using this as an opportunity to remind you of our other integration strategies. So the first one was integration by parts. This one, Henry, this is what you tried to do a second ago. This is partial fraction decomposition. So I'm trying to integrate this. So those of you that just walked in, like, notice it's not a real big change from what we've done. Like, the upper limit here is infinity. So technically, again, the most precise way of writing it is to say, like, b is approaching infinity and we're integrating from 0 to b. So we're still going to find this antiderivative. We're still going to substitute in the upper limit, substitute in the lower limit, but then we're just going to take the limit as b goes to infinity of that answer. Okay? So try this one. Remind yourself of partial fraction decomposition. I'll give you a couple minutes. Okay, time's up. Time's up. Ready? So first, partial fraction decomposition. So 2 over x plus 3, x plus 1. Is a over an x plus 3 plus a b over an x plus 1. And do I need to review this? Are you good with it? Thumbs up? Yes? Good? So we can multiply through, we can rearrange, we can figure out the coefficient. What does a turn out to be? And b? It's -1, which means this original problem could be rewritten as the integral from 0 to infinity of 1 over x plus 3 minus 1 over x plus 1. Did I write that wrong? Yeah, a is -1. Yeah, I think, so it should have been that. So it should have been that, sorry. Like, so when I asked you what a was, I just was remembering it was 1 and -1, but notice it would matter which factor I wrote a over, right? If you would have written a over x plus 1, then we would say it backwards. Okay. Um, Focus with me. So really, I need to break this apart into two different integrals. Antiderivative, antiderivative. Should they be absolute values? Yeah, so really when we're thinking about it, because of the 0 to infinity, we wouldn't even need to think about it because everything's positive here anyway. So this needs to be evaluated from 0 to infinity, and we need to add this thing evaluated from 0 to infinity. Now here is where writing infinities might cause you some issues, because when you look at this, like if you wrote this down, so don't write this down. If you wrote negative natural log of infinity, and then you're over here, you're going to write a natural log of infinity, like, then this is where you'd end up saying like an infinity minus infinity, really, right? Like, and so, but that is an indeterminate form. So do we actually know what infinity minus infinity is? No, like that actually means we have it written in a way that we can't tell the answer. So where it is an advantage to write this in the following way. So I'm going to say I need to go and write the limit as b approaches infinity of this whole thing, natural log x plus 3 evaluated from 0 to b, plus the limit as, I don't know, c approaches infinity of the natural log of x plus 1 evaluated from 0 to c, something like that. Now, I guess really I don't need two labels. Are you okay if I make everything b? Because it's the same value, so I might as well just make it all b's. I think that would actually make this a lot clearer. Now, remember, infinity and minus infinity, indeterminate form, which means I don't know the answer, which really means I need to look at it in a different way to see the answer. So if I wrote this out, think about what I'm writing. I would say the natural log, negative natural log of b plus 3 minus a minus natural log of 3. And that's the thing I need to take the limit as b approaches infinity. But if this thing is also the same limit, I'm just going to keep going here and say substitute in b, so that's plus a natural log of b plus 1, and then this would be a minus natural log of 1. So I'm just substituting an upper limit minus lower limit. And again, I can still see the infinity minus infinity that's sitting here, which means it's in a form that I need to rewrite. How could I combine those together? Am I writing what you want me to? How do you do? Properties of logs. The log of a over b is the log of a minus the log of b. And what do we have left? This is 0, and this is a natural log of 3. Now b goes to infinity. You can get this answer now. If b is going to infinity, this is actually approaching what number? 1. Right? So think horizontal asymptote. Like that's what I go back to. Like think pre-calc. The degrees are the same, right? If I go to infinity, should I just divide the leading coefficients here? So this whole thing just is becoming a 1. What's the natural log of 1 again? This piece drops out. So the final answer, it's sitting right here, natural log of 3. The problem with L'Hopital's rule is that we don't have a single fraction, right? We're taking the log of a fraction, so we couldn't really go inside of this logarithm to use L'Hopital's rule. So now, in some respects, I guess you could kind of think that way if then you would take the logarithm after the fact. So I guess if that's what you're thinking, so if you say, what's this inside doing? Yeah, you could think about L'Hopital's rule there and get the answer of 1. Now the natural log of 1, there's 0. So that's fine. I think I misinterpreted what you meant. So I'd probably point out on this problem, you could probably not do this blue step here and write the limit. But if you get that infinity minus infinity, like a lot of you were tempted to say 0 or infinity in that moment, right? And that is the benefit of writing the limit. It's going to force you to do the other things that we've learned and get to a result. Let's try one more, and then we'll be done for the day. That's it. You can make 2 integrals. Yes. The box did suggest it, if that's what you're meaning. Time's up. Let's see how we're doing. Time's up. So, split into 2 pieces. So you can choose whatever you want here, but wouldn't 0 be rather convenient? So you can put 1.5 there if you want. The problem is going to be you're going to have to know the inverse tangent of that number that you're going to say. So choosing a value that's on the unit circle would be, or at least labeled on the unit circle nicely, would be helpful. So here, I just have my 2 limits. I've just changed my lower and upper limit. No work's really happening. Here's the inverse tangent, which is the antiderivative. We're going to substitute from a to 0, and then over here from 0 to b, and have those limits. Substitute upper limit minus lower limit. And so really here is something that you would need to know what the graph of the inverse tangent is about. Like, it's the inverse, right? Like, it's the function that would undo the tangent. It's the function who takes the ratio and gives the angle. If x goes to infinity, what's the y value for this graph? It's pi over 2. There's a horizontal asymptote, right? So when you think about the tangent graph, so if I put the tangent graph here, zoom in. Isn't there vertical asymptotes at every pi over 2 interval here, right? And so when we think about like the tangent graph here is not 1-to-1, right? Fails the horizontal line test, that we had to restrict it. And the restriction, if you remember, so all this comes back around at some point, it's fourth quadrant and first quadrant, so minus pi over 2 to pi over 2 for that restriction. And so notice then, if there's a vertical asymptote at pi over 2, if you switch the x and y's and solve for the new y, shouldn't there be a horizontal asymptote at pi over 2? That's the connection. So that means that we know this answer, and we know this answer. And the inverse tangent is 0 is 0 because the tangent of 0 is 0. Final answer is pi. This would be a no calculator question. Siri had a good question, so then we'll wrap up. But why am I using two different variables? Do you notice that here we're not approaching the same value? So since one is negative infinity, one is infinity, that's why it shows them. It wouldn't really change your work. It could look confusing if I have in the same line b's and one is negative infinity, one is approaching positive infinity. So that's the reason. Okay. So this is. Oh, I said I would show you the nice summary for the vertical asymptote that I meant to that I didn't have written out there. And so notice here it's really the statement that I was talking about, that we're just going to look at the interval, and if there's a problem in the interval, vertical asymptote, then we need to write a limit to approach the vertical asymptote. I did have one additional example here to give with that. But we're kind of out of time. I'll put it up on the screen if you want to practice to take with you. You done with this? I'll wait a second. I would pay attention, like for this, like something to jot down in your notes, is pay attention to the direction of the limits, approaching from the right or the left. Okay. Sometimes that might matter because when we think about finding a limit that, you know, approaching from one side, maybe I get a number and the other side I wouldn't, right? So you have to notice from the left or from the right for these questions. So here is the example. So I'll put the question up. So if you want to try it, and I'll put the answer up after it. So if you want to see if you can get it. Here's the function. So there's the integral. What method did I include in this one? It is a use substitution. 2x plus 2, there's a factor of 2, bonus 2, you can deal with that, fix it. So notice though, do we have a problem with this in terms of the domain? Like what's the domain issue for this function? It's 0, but 0 is a limit, right? So that's where we're going to need to have a lower limit to be a value, like b, and say the limit as we approach b from the right or from the left? It'd have to be from the right. It's toward the interval, right? We're going from 0 to 2, so it'd be from the right. And so evaluate it, see if you can get an answer. So here is my solution worked out even here. So if you want that to compare your work later, you can do that. Okay. So you can see there is a solution to it. Okay. There's a My Math Lab for this. This is 9.4. Remember, we skipped that section. Okay. So, chapter 10, you should be probably at least an attempt down at this point if you haven't finished it. have one to go, it would be a good place to be. If you haven't done either, you're probably behind. And so Thursday before class starts, they're due. Okay. Thursday, I'm going to start chapter 11. My goal is to, by the end of March, to be done with chapter 11, starting the review April or maybe a little before that. So we have one more test. Okay. Questions on that? Anything about what you need to do? You had a quiz that you should have done. Okay. All right. I'll see you.